The following Zoom session is being recorded and will appear later today on my YouTube channel, Math with Mayo. There are two different classes that may be observing this session. Therefore, when you participate in the Zoom meeting, if you do not wish for your picture or your name to be made public, please leave the video off and use an alias name. If you have questions during the meeting but do not wish to speak, email me at bmayo@ybcc.edu and I will respond as soon as I can. All right, so today we start a new chapter, Chapter 8. All of you should have received a PDF file of Chapter 8 in your email box. If you did not receive one, please email me and I will send it out again. Anyway, so let's get started. So this is section 8.2, part 1. We'll be spending tomorrow on this as well. I want to start out with an illustration involving some people. How about Jose, Mary, Ralph, Ben, and Susan. Okay. And let's pick some dates. It just so happens that Jose's birthday is April 2nd. Mary's birthday is March 3rd. Ralph's birthday is September 12th. Ben's birthday is also September 12th. And Susan's birthday is June 4th. So there are several things we know about people and birthdays. Everyone has exactly one birthday, discounting religious experiences, of course, but everybody has one birthday. Nobody has more than one birthday. Several people can have the same birthday, as in Ralph and Ben. That doesn't mean Ralph and Ben are twins necessarily. They may not even know each other. But again, everybody has exactly one birthday. More than one person can have the same birthday. What does this have to do with anything? Well, this is the same way that something called a function works. Oops, function. Okay. I want to point out that function starts with the word fun. So here we have a math term that's fun. Woo. But it ends with shun. We all know what it is to shun someone. Anyway, all right. Let me read to you from the textbook. This is on page 614 of the hard copy of the textbook. This is what it says about a function. It says a function is a set of ordered pairs in which to each first component there corresponds exactly one second component. In other words, everybody has exactly one birthday, everybody being the first component and their birthday being the second component. The set of the first components is called the domain of the function, and the set of the second components is called the range of the function. So back here, this would be the domain, and this would be the range. Okay, so for a function, we've got the domain and the range. It's also the input, the x values. This would be the output, the y values. This is the independent variable. This is the dependent variable. This is the first, let's see, first coordinate and the second coordinate. All right. Or cause, have this cause and effect. So these are all different ways of describing the same thing to do with domain and range. Input, x value, independent variable, first coordinate, cause, output, y values, dependent variables, second coordinate, effect. And we'll talk more about that as things go along. All right. So what I want to do now is take a look at some examples. This says, find the domain and range of each relation. Okay. And we have the following set of ordered pairs. Okay, so we have a set of 4 ordered pairs. The domain would be the set of all the x values, and I'm going to write them in order from smallest to largest. The range would be all the y values, and again, I'll write those from smallest to largest. Oops. Anyway, those are hard things to make. Obviously, one last try. Need to slow down. There we go. Anyway, so for the following relationship, given there, the domain is all the input values or all the x values. The range is all the y values or output values. Any questions about that example? Okay. Take a look at this scenario. And we have the following correspondence. It says, determine whether the relation defines y as a function of x. Y as a function of x. So this is x and this is y. Find two ordered pair. If it does not, find two ordered pairs where more than one value of y corresponds to a single value of x. So either it's a function or it's not. And if it's not, list one of the contradictions. Well, for this, each input, each x goes to exactly one y or output. So this is a function. Okay. Now, how about this one? Let's see here. -4, -2, 0. 6, 8, 10, 12 with the following correspondence. This is not a function. And why not? Because 0 goes to 10 and 0 goes to 12. So here we have the same input going to 2 different outputs, just more than one different output. So it's not a function. Okay. Any questions about that? Okay, let's see here. So we have the ordered pairs -2, 4, -3, 8, -3, 12, -4, 16. Yeah, let's make that a little nicer. So is this a function or not? The answer is no, because -3 goes to 8 and -3 also goes to 12. So you've got the same input going to more than one output. So no, it's not a function. Okay. How about this example? Is this a function or not? Yes, it is. You can have 4 different people with the same birthday. Okay. What's that? Quadruplets? If they were all born same time, same mother. Anyway, but you can have more than one input going to the same output. You just can't have it the other way around. So for instance, let's say this situation. Oops, that's not what I wanted. This would not be a function because you've got one input going to more than one output. Any questions about this at this point in time? Okay. Now, let's talk about function notation. Okay, so y written in function notation is typically written looking like this. We've sort of got an italicized f and then parentheses and an x in it. So y equals, we call this f of x. Now, this is a bit confusing. It's function notation. Looking at it, it looks like f times x because there's parentheses around the x, and we're taught that that grouping symbol can imply multiplication in this case, but it's not multiplication. Also, if you read its long description would be f is a function of x, but we abbreviate that and say f of x. Well, back in pre-algebra, if you took it, you learned that in to do with percentages, oftentimes of becomes multiplication. What is 4% of 12? So f of x also sounds like f times x. Well, it looks like multiplication. It sounds like multiplication, but it's not multiplication. This is a single symbol representing y, but telling the world that it is a function. So it behaves according to function rules. All right, now, suppose we have the following equation. Y equals 3x minus 5. And we want to make a table of ordered pairs corresponding to this equation. How about we let x be -1, 0, 1, and 2. Okay. Now, how do we find the y values? We plug in the x values here. So when x is -1, y equals 3 times -1 minus 5, which is -3 minus 5, which is -8. When x is 0, y equals 3 times 0 minus 5, which is -5. When x equals 1, y equals 3 times 1 minus 5, which is 3 minus 5, or -2. And finally, when x is 2, y equals 3 times 2 minus 5, or 6 minus 5, which is 1. So those are some ordered pairs corresponding to the equation y equals 3x minus 5. In fact, that's a linear equation, and we could plot those points on a graph and it would form a straight line, going back to what we looked at in beginning algebra in chapter 3 of this textbook. Now, can you see that for each input value, there's a different output value? This equation is also a function. So we could write it like this: f of x equals 3x minus 5. Okay. Actually, I'm not going to do that. I'm going to do this. Now, using function notation, I'm going to find the same ordered pairs. I would say f of -1. What does that mean? That means -1 goes in the place of x. How do I find f of -1? The same way I did over here. That would be 3 times -1 minus 5, which is -8. So f of -1 equals -8. This is the function notation of writing this ordered pair. Okay. F of 0 would be 3 times 0 minus 5, which is -5. So f of 0 equals -5. This is the function notation corresponding to this ordered pair. And likewise over here, these ordered pairs, if we didn't write them in a table, they would look like that, etc., etc. All right. Any questions about that? So in fact, I could go on and say f of 1 is going to be -2 and f of 2 is going to be 1 because I already calculated their values over there. All righty. Now, let's say we have the following function. F of x equals 2x minus 3. they want us to find, whoops, f of x, sorry. They want us to find f of 3 and f of -1. So to find f of 3, we put 3 in the place of x. So f of 3 equals 3. That corresponds to the point 3, 3, with the coordinates of which are 3, 3, and that's a point on the graph. Okay, f of -1 is 2 times -1 minus 3, which is -2 minus 3, or -5. So here again, we have a ordered pair. The input is -1 and the output is -5. But in function notation, we would say f of -1 equals -5. Any questions about that scenario? Okay, how about this one? G of x equals x cubed minus x. Well, hold on. What do you mean G of x? Well, just like typically when we're dealing with variables, we use x and y, we can use other letters as well. Well, typically when we're dealing with function notation, we use f of x, but we can have other values as well, other letters. For instance, if this was a business algebra class, we might talk about profit functions, which would be P of x equals something, cost functions, C of x, revenue functions, R of x, okay? So the fact that we're using G of x just means it's different from some function that's f of x. Anyway, G of x equals x cubed minus x. We are asked to find G of 2 and G of 3. So to find G of 2, we're going to replace all the x's in the original function with 2. So I get 8 minus 2, or 6. So G of 2 equals 6. G of 3 would be 3 cubed minus 3, which is 27 minus 3, or 24. So G of 3 equals 24. Any questions about that situation or these examples? Okay, let's take a look at this scenario. We have h of x equals 3 divided by x minus 4. We are to find h of 5 and h of -2. So h of 5 would be 3 over 5 minus 4, or 3 over 1, or 3. So h of 5 equals 3. So if we were to graph this function, one of the points on the graph would be 5, 3. h of -2 equals 3 over -2 minus 4, which is 3 over -6, or -1/2. So h of -2 equals -1/2. So the point with the coordinates -2, -1/2 would also be a point on the graph of h of x. Okay, let's take a look at this example. H of x equals x squared plus x minus 2 all over x squared minus 5x. We're going to find h of -2 and h of, h of 5. Okay, so if x is -2, we get the following. -2 the quantity squared plus -2 minus 2 over -2 the quantity squared minus 5 times -2, which is, let's see, -2 the quantity squared is 4 plus Negative 2 minus 2 would be negative 4, which would be 0. In the denominator, negative 2, the quantity squared is 4. And then minus 5 times negative 2 would be plus 10, which is 14. But 0 divided by 14 is 0. 0 divided by any number other than 0 is 0. So 0 divided by 0 is something different. We'll save that for calculus. But 0 divided by a non-zero number is 0. So h of negative 2 equals 0. Let's find h of 5. That would be 5 squared plus 5 minus 2 over 5 squared minus 5 times 5, which is 25 plus 5 minus 2, which is 30 minus 2, which is 28. 5 squared is 25 minus 5 times 5, which is also 25, which is 0. But 28 divided by 0 is undefined. Okay, so h of 5 equals undefined. What that means is that 5 is not in the domain of this function. It's not an acceptable input, because when we put 5 into the function, we do not get something real as a range value or a y value. So we would say that 5 is not in the domain of h. More about that later. Okay. Now, let's say that g of x equals 2x. Okay. So g of 4 would be 2 times 4. G of negative 3 would be 2 times negative 3. How about g of star? Well, that would be 2 times star. How about g of Barbie? That would be 2 Barbie. Or how about g of Ken? We'll bring Barbie and Ken into this. That would be 2 times Ken. Okay. So whatever is in here gets put in there. Okay. So what would g of w equal? Well, that would be 2w, because w goes in the place of x. What about g of w plus 1? Well, now w plus 1 goes in the place of x, so we'd end up with 2w plus 2. So again, g of that equals 2 times that. Whatever's in here gets put in there. Okay, don't overthink it. All right, now we're going to go backwards, and that is that instead of putting in an x and finding a y, now we're going to put in a y and find an x. All right, so let's say we had the following equation: y equals negative 2x plus 5. And we were told that y was 5 and y was negative 7. Okay. How would you find the corresponding x values? Well, you'd take this and put it in the place of y. So you'd have y equals negative 2x plus 5. And then you'd go back and solve for x. So solving this, let's see, we'll subtract 5 from both sides of the equation, and we'll divide both sides by negative 2, so x equals 0. Okay. Suppose y is negative 7. Well, then we'd have negative 7 equals negative 2x plus 5. We'd subtract 5 from both sides. Negative 12 equals negative 2x. Divide both sides by negative 2, and x equals 6. Okay. Any questions about that? So here we're putting in the y value and finding the x value. Now let's do the same thing, but using function notation. Okay. Suppose we have, let's see here, f of x equals negative 2x plus 5. And it says, for what value of x does function f have the given value? First of all, it says f of x equals 5. So that corresponds to what we did over here. So if f of x equals 5, that's going to go in the place of f of x. It's not the place of x, it's in the place of f of x. So we'd have 5 equals negative 2x plus 5. This should look very familiar. 0 equals negative 2x. Divide by negative 2. X equals 0. So for what value of x does f of x equal 5? For x equals 0. And then this second scenario where it says, let's see here, let's get rid of that, where it says, for what value of x does f of x equal negative 7? So we would put that in the place of f of x. Negative 7 equals negative 2x plus 5. We subtract 5. Negative 12 equals negative 2x. X equals 6. So let's see, for what value of x does f of x equals negative 7? For x equals 6. So again, we're doing the same thing we did in the past, again in chapter 3, back in beginning algebra. Given an x, plug it in, find y. Given a y, plug it in, find x. But keep in mind, let's say for this function, x replaces what's inside. Y replaces the entire thing. Okay, so x is the input and y is the output. Okay. Let me give you a couple of more scenarios going back to the idea of a function. Okay. Let's say we have the students in this class. Students in, let's see, math 093. And over here we have bags of potato chips. Let's see, is it TOE or TO? Bags of potato chips. Okay. So over here, each bag has a specific weight. Okay. Actually, let me think about this. No, I'm not doing this correctly. Sorry. I want it's mixing two ideas together. Over here, we've got bags of potato chips. We'll get to class people in a minute. Potato chips. And over here, we've got weights. So these are bags of potato chips on a shelf, and these are given weights. So does this describe a function? So the question is, does each bag have exactly one weight? Or would a bag of potato chips have two different weights? Now you could say, well, if you open it up and start eating the chips. No. Just at a given time, does each bag of potato chips just have one weight? The answer is yes. So this is a function. Okay, I know that was a little confusing. Sorry. Let's do a different one. Let's have band members and instruments. This is the band, this is the math let's see, maniacs. I don't know how you spell maniacs. We'll call it the math musicians. Maniacs. Math musicians. Okay, so over here we have math musicians. Math musicians. I can't talk today. Over here we have instruments. Function or not? Probably not, because a lot of musicians can play more than one instrument. So if you had one person over here that could play two instruments over there, that would not be a function. Okay. I don't know if that's helpful or not. Anyway, so for tonight, your homework, section 8.2, part 1. Again, if you didn't get the chapter 8 PDF file in your email box, email me and I'll send it to you and then call you to make sure that you're getting it. Other than that, I'll be back at 1:15 with an office hour. So have a great rest of the Monday and we'll see you later.